Uh, so all that I showed in that video mostly was the same thing, moment redistribution, and how we can reduce the amount of negative reinforcement required. Instead of doing manually, I was just showing how we can do it in the SP Beam software. So that's all. Now we will start this topic, two-way slabs. So design of two-way reinforced concrete slabs. Okay, so we will go over an introduction. We will go over mechanism of action, how they carry and distribute the load, and also some of the design methods for two-way slabs. So what are slabs? Slabs are actually plate elements which are used for flat surfaces such as floors and roofs. So plate elements, that means they carry the load by bending like a plate. Plate bends in two directions, in two perpendicular directions. Plate undergoes bending, and that's how they carry the load. So it is stronger and stiffer than bending in one direction alone, and it is not the same as bending independently in two different directions. Okay, so yeah, so this could be supported by beams, masonry, or RCC walls. It could be slab on grade, like in the ground, or supported by columns. Okay. So let's go over some different types of two-way slabs. So one is flat plate, where you directly have the slab sitting on columns and nothing else. Okay. So flat plate is usually very aesthetically pleasing. You have large spaces where you only have your slab and column and nothing else. Then the other, it is somewhat bold concept of design, because there has to be a lot more care taken in designing flat plate than the other kinds of slab. Especially the chances for punching shear is much higher for flat plate. Then the other type, two-way joist or waffle slab. So you can see that you can call it either, you can imagine that you have joists going both ways, as you can see here, or you can imagine this like a waffle. Where so you have ribs going in both ways. So that is a waffle slab, and above each of the columns there is some part where the concrete is filled in. This is again to ensure resistance against punching shear. And next you have two important components that you can see here. One is a drop panel. So drop panel is like a portion of the slab which has been thickened above the column, and the column capital, where you have a prismatic shape. Which is where the cross section is tapering towards the column cross section. So again, drop panel and column capital will greatly increase the resistance to punching shear. And then you have flat slab with beams in the other case. So what are some of the advantages and disadvantages? So two-way slabs, you can have long spans carrying heavy loads without beams, so you can have additional roof space since you don't have any extra beams or girders. So you are utilizing the maximum bending in both the directions simultaneously. So both directions reinforce each other. So it is economic in terms of both the amount of concrete and amount of steel required. Particularly the waffle slab design is more economical. It is stiffer and stronger while also using less material, and it has an attractive appearance as well. The disadvantage usually for two-way slab is that the form work is more expensive to lay out the slab, to pour the slab. The fire rating is lower, and if you have large lateral loads, then it is better to have a separate lateral load carrying system, such as a maybe braced frame or a shear wall or some other arrangement. Just a second. So let's just recall about something, general points about design as opposed to analysis. Design problem does not have a unique solution. So you have to, we have to iterate several times before we can arrive at a satisfactory design. And different engineers may come up with different solutions for the same design requirement. But the basic SS, the three SS you can say of design, those are strength, stability, serviceability. Just a second, let me just plug this in, just a second. Strength, stability, and serviceability, which we have learned earlier. There is also one more S, that is structural integrity. Again, we don't specifically discuss structural integrity in undergraduate class, but here, hopefully, in one of the, before we finish, we will discuss this topic also. Economy, and we are using limit states design for all our design in this course. Okay, let's see what is one-way action versus two-way action. Okay, so in some cases, it is very straightforward to say that the bending will be only in one direction. For example, you see the case here. Unsupported, one of the edges is unsupported and the perpendicular edge is supported, then there is only one direction in which the bending will take place, that is along the longitudinal direction. then this has to be one way. Another case where we can say that it is one way action is the second case. Why it is one way here? Now, look at, so in this second case, mostly the bending will only take place in this vertical direction. Okay, I put that as in X, just following textbook, but let me explain. Only in this direction, very little bending in this direction. Why is that so? Just give me 1 second, I will come back. I just need to use the restroom. Just 1 minute, I will be back.
Dr. Nathan, if you're talking, you're muted.
Oh, thank you so much, Mercy. Yes, you are correct. Thank you very much. And now I was saying, thank you. There is a simpler way in which we can understand when it is very long in one direction, what makes it one way. For example, here you can see that when it's really long in one direction, the moment that is being carried in that direction is very small as compared to the moment being carried in the short direction. So bending in the short direction is the one that carries a majority of the moment. Okay, and so if you can see, okay, here is the explanation for that. Now consider these two strips. S1 is the strip in the short direction. L1 is the strip in the long direction. Now these two strips are intersecting at this location, right? Like this common rectangle. Now, when this bending is happening, you can imagine that this particular point is getting displaced down, right? So how will the loads distribute? So let's say that we are applying point load at that particular location. How will this point load get distributed between S1 and L1? So one thing you can imagine is that the downward deflection is same for both, right? Okay. So your what is the downward deflection? If you just use some kind of a deflection formula, like what you all may remember from serviceability, like maybe for a uniformly distributed load, EI, this thing, then you can get roughly that in the direction A, WA LA to the power 4 is equal to WB LB to the power 4, right? Roughly. So that means WA by WB is equal to LB by LA to the power 4. So in how much load if the shorter direction is half the length of the longer direction, then it will carry 2 to the power 4. So that is 16 times more load. So did you see? It's because of the large difference in stiffness. So this is still not accurate analysis, but very roughly, it gives us the explanation. See, anytime, let's say that you have a bed. This is my bed, and it is resting on, let's say, springs. So I have two huge springs at these two ends. And let's say just 2D, okay, 2D. And in the middle, these two red springs are, you can imagine, thick metal springs. And in the middle, I just have a foam block. Now, when we put any load on this bed, that is when we lie down or something, then almost all the load will go to the springs, right? Because they are much stiffer than the foam block. And if your bed is rigid, if you're thinking it is rigid, then it will compress everything through the same distance. So for the same displacement, the stiffer ones will offer a much higher load at the support. So the load is distributed in the ratio of the stiffnesses. So therefore, your shorter direction in bending will carry much higher moment than the longer. That's why when your long edge and short edge are relatively similar length, that is, they are not too different in length, both of them will carry significant bending. So your bending in both directions is very significant this way and the other way too. So that is two-way action. Okay. Okay. Now the way in which the load gets distributed towards the uh, edges is also different. Like we said, in one-way action, the supporting load is almost all going to the whichever direction majority of the bending is, that direction will take the maximum loads at the supports. And in the two-way action, the distribution is according to a trapezoidal tributary area. If you notice here, the way you draw it is you draw 45-degree angles from all the corners. You draw a 45-degree line from each corner, and wherever they intersect, you form a triangle. And your trapezoidal load goes to the long edge, triangular load goes to the short edge. Okay. Okay. So, what is the reinforcement layout? So, of course, uh, you are having bending in both directions. So you need flexural reinforcement in both directions. And plus you need a special additional reinforcement for two-way shear. So as you can see in the corners where the columns are, uh, you will have uh, you will have additional reinforcement to account for two-way shear. Okay. Okay. So So in the ACI code, any method which satisfies equilibrium, mechanical equilibrium, and geometric compatibility can be used. Okay, and the two most popular methods for design of two-way slabs, those are direct design method and equivalent frame method. And slabs on ground are excluded in this particular clause, and it is only floor slabs. So the beams should be located on the panel edges to be able to use these design methods. And if there is a wall is just assumed to be a beam of infinite stiffness. Let's go over direct design method. And it is a semi-empirical method. It is based on experiments by Jirsa and other researchers, and it is only used for gravity loading. Uh, Let me open one of the older codes. So just to show you that the older code, it does have the direct design method explicitly laid out there, uh, unlike the later codes. So here is ACI 318 2019. Now we will compare that to 2002 here. So let's go let's go here first to chapter 8. Just a second. Okay, so you can see here so slabs shall be permitted to be analyzed for gravity loads in accordance with A or B. Direct design method for non-pre-stressed slabs, equivalent frame method for non-pre-stressed and pre-stressed slabs. So okay. So code provisions up to 2014 contained use of direct design method and equivalent, but these methods are well established and covered in available text. The provisions for gravity load analysis have been removed because they are considered to be only two of several analysis methods, and however, the direct design method and equivalent frame method of 2014 code may be used for the analysis of two-way slabs or gravity. So it says that it is not explicitly mentioned in the 2019 code, but we can still use it as described in the 2014 code. Okay, so let's go to 2014 code. We need to look at 2002 code. Here you can see these two sections, they are not there in the 2019. It ends at 8.8. But if you go to 2014 code, section 8.10, okay, so here is very clearly given the direct design method. So direct design method is a set of rules for distributing the moments to satisfy safety and serviceability simultaneously. Now, now there are some clauses for the there are some constraints or limitations, and the direct design method can only be used in those cases. Okay, what are those? You shall have at least 3 continuous spans in either direction, in the both perpendicular directions. Then successive span lengths measured center to center of support shall not differ by more than 1/3 the longer span. Okay. Panels should all be rectangular, and the ratio of longer to shorter should not exceed 2. Okay. And column offset shall not exceed 10% of the span in direction of offset from either axis between center lines of successive columns. And only gravity loads, no lateral loads. Like you cannot have lateral load and the slab carrying the load by diaphragm action. You cannot design that by direct design. Okay. Now let's go to the different details. There are a lot of details here. Okay. Let me reopen my file for the pictures. Okay. Now, first one is a minimum thickness requirements. So this is similar to beams, where to limit your deflections, you need to have some minimum thickness of the beam. So if you all remember, that is covered in okay, I need to reopen. Okay. So if you remember in the undergraduate class, when you study beam design, there is a minimum depth assigned to non-pre-stress beams so that your deflections are limited. Okay. And we also saw it in when we did our serviceability review using some advanced or more detailed problems. We see that there are some limitations to the, there are some caps to the thick or minimum thicknesses required for the beams. Similarly, in the two-way slabs, we have some minimum slab thickness to limit deflections, and that is based on the condition with drop panel, without drop panel, depending on what condition we have, the minimum thickness requirement is different. Okay, like for example, you can see that for when you do have drop panels and edge beams, then you are allowed to have slightly thinner slabs, as you would expect, because those are limiting the deflections.
But can you really be sure about this thickness and table? Because it's just an assumption. You really never know how much load you're going to have, like in real life, you know?
Yes. So, yes, definitely. Now, it it depends on your service load and the your reinforcement and your slab thickness will ultimately be adjusted for your load. This is your first starting point in the design to assume the thickness. And as you go through the design, if your loads are especially high, like anyway, if it is some non-standard kind of loading like heavy machinery and so on, then we need to do the detailed serviceability calculations as we saw in the beginning when we were doing serviceability.
Yeah.
We do need to explicitly calculate deflections. That's absolutely right, to make sure that you know the deflection requirements, as you're saying, they depend also on the use of the building. Like if there is some very sensitive equipment there, maybe they want under quarter inch or something. So then you need to make sure of that. You need to adjust your design accordingly. Maybe you may even need to go for pre-stressed slab where you will have very little deflection.
Because I was reading this paper, they had a list of reasons why the ACI code for minimum thickness should be updated.
Oh, okay. Please, can you refer me to this paper?
Yeah, I'll send it to you.
Thank you so much. Because I'm trying to always update the material based on the latest papers. Most recently, even in the steel design, based on, I think those of you who took the advanced steel design, you may remember, for beam column, we use the equivalent axial load method. Based on that paper was just published in 2019, I remember. So thank you very much, Mercy. It's very important, the point that Mercy is saying. The codes are continuously evolving, and the design methods are also continuously evolving. A lot of times it is seen, for example, in serviceability, you saw that, oh, it might seem like, it's okay, it's just taking an average of, average moment of inertia of the member. But in some cases, it will make a big difference in the amount of deflection that you calculate. So the code is being updated always according to the latest research, but we have to keep track of that as well. Okay. Now there is one more point here, how the moments are apportioned between the two directions. Okay. For example, let's say for that, let's go back to this figure. Okay, compare these two. Now it is different than what you see here. Like in the left-hand side figure, you see that, okay, there is just a common point of intersection. So some load goes to the long strip, some load goes to the short strip. But actually it is more complicated than that, because now you can see that, for example, see the strip S2, Now you can see the L2 now, and S2. You can focus on L2 and S2. Now, when S2 has to bend in this way, then if S2 has to bend in this way, correspondingly in the corresponding point, intersection point in L2, it has to introduce a twisting, right? For S2 to be able to freely bend like this, it has to twist the section at L2. So did you all get that point? Maybe I can draw it. See. let's say before bending, this is S2. I'm drawing the view from here. Now take this section, and L2 is L2 is of course passing through like that, right? Now just take this block. L2 is going like that. Now, when S2 bends, this piece will rotate like this. That means for the red beam, rotation like this in between is like a twisting. So the S2 cannot bend as freely as if it were just independent bendings in the two directions. The bending in one direction also makes it stiffer in the other direction. So do you see? It's not just like you have one beam bending this way, another beam bending this way, and you just add up both of them. No, two ways is much stiffer than that, because the bending in one direction is greatly increasing the stiffness in the other direction as well, because of torsional effects, torsional restraint. Okay, so that way, if you see, for independent action in two directions, you have, this is just WL square by 8, right, in each direction. But it is not, it is actually 0.048. So 1/8 is 0. If you do WL square by 8 and do half of it to each, it will be WL square by 16. But that's not. You will have each of the moments will actually be only 0.048 WL square. So that you can get from an exact analysis, but in the direct design method, we will follow a semi-empirical distribution of the moments. So how to do this? So first step in the direct design method is to determine the
Dr. Nathan, excuse me. How do we calculate that twisting prevention of the other beams?
Yes, we don't explicitly calculate that. If we want to were you? Sorry, Mohammed. I think. Oh no, you were not speaking. Okay, there was some kind of disturbance. So we are not explicitly calculating. That point I was just making to stress that it is. If you just assume, if you just think of two-way action, that, oh, there is bending this way and bending this way. So if I do bending this way and if I do bending this way separately, and if I add the contribution from both of them, then that is equal to the load carried by two. No, because the problem is more complicated than that, because the bending in one direction is not independent of the bending in the other direction. The stiffness in one direction also makes it stiffer in bending in the other direction due to the torsional restraint. Now, the exact calculation for the moment that is carried, we need to use theory of elasticity, and we need to solve the stress equilibrium equations for plate. That's the minimum we need to do. Then we can get the 0.048 WL square, that value. Or if not, lot of times nowadays with the use of computer programs, it uses finite element method for analysis of the two-way slabs.
Oh, okay, thank you. I know that the computer analysis, because I just thought it's like bending a spring that help the moment of inertia of the beam that want to deflect. I thought maybe we can add some amount to the moment of inertia of the beam in one direction and reduce the deflection.
Oh, yes.
It's like bending a spring, which are on the two side face of the beams. Kind of
Yes.
like helping.
Yes. Actually, the point that you are saying, it is somewhat the basis for equivalent frame method. So when we are doing equivalent frame method, we will use explicitly, we will do some calculation for the contribution from torsional restraint. We will consider twisting moment of inertia in that direction and add that stiffness to bending in the other perpendicular direction. We will do that explicitly actually when we do equivalent frame method. So yes, we are going to do it.
Thank you.
So the first step in the direct design method is to get some values for the positive and negative moments, and this is based on the distribution factors again. Now, based on end conditions, we can assign from m naught. So m naught will just be WL square by 8. And now W is, you will take as yeah, I'm just coming to that. What is m naught? Let's say we are doing bending in the short direction, suppose. Suppose we are doing bending in short direction. Then how will you take m naught will be Q. Q is the PSF, the area load. W is line load, but this is area load. So you will do Q times long direction. We used short direction, let's take B. Long direction, let's take A. So if you're doing bending in short direction, you will do QLA LB square by 8. And if you were doing the long direction, then your M naught will be QLB LA square by 8. Because it's just like that's your slab. And if I'm bending like this, So this is my long direction, LA, LB, and so if you're bending that way, then your Q is the area load, and this is your width. So therefore, if you convert it to a line load, you will multiply by the width in the other perpendicular direction. So this multiplication is just to convert the Q to a W. Okay, so that's how you will get M naught for bending in that particular direction. And then you will get the positive and negative moments using these moment distribution factors. But now we need to, in the bending along a certain direction, it is not just a uniform. The moment is not uniformly distributed across the width. Like if you consider the entire width of this, then your moment is not uniformly distributed across there. Moment is more in certain regions of this strip than other regions. So therefore, this is analyzed as, it is divided into two types. One is column strips, that is the region that is closer to the columns, or specifically 1/4 of the shorter span from either direction of the column center line. So this is defined as what we call as column strip. And in between the column strips, what you have is known as middle strips. Therefore, the column strips, as you would imagine, they are stiffer due to the restraint to deflection offered right around the columns, due to the greater stiffness around the columns. So therefore, they carry a greater moment. Okay, so we will distribute those positive and negative moments in between the middle strips and column strips. So here, for example, is using finite element method, you can get some idea of how the moment is being distributed between column strips and middle strips. For example, just a qualitative explanation here. You can see your moments are a bit less in the middle strips, in between the column strips, for both X and Y directions. Okay. Now how to distribute to column strips. So, okay. So the distribution to the column strip is based on the relative stiffness of the beam and slab. Okay. So how much goes to beam, how much goes to slab? And okay, so this part, it is there in some empirical way, even here. Sorry, Mohammed, actually I forgot this point. Even in equivalent frame method, we explicitly use the torsional stiffness to, as you said exactly, boost the moment of inertia in the perpendicular direction. But it is there even in direct design method, although in a more empirical way. So the distribution along the column strip, you have a beam. So out of that, how much goes to beam and how much goes to slab? So that is based on relative stiffness of beam and slab. So based on this alpha F value, as you can see here, this is the beam flexural stiffness divided by slab flexural stiffness. If you recall, EI is the flexural stiffness. No, EI by L, but L is the same. Now how to distribute these moments. Now you have interior negative moment, exterior negative moment, and positive moment. So this table from my ACI code, it tells us out of the first step we did was we got this positive and negative moments, right? But this, for example, if we see interior negative moment, this is 0.75. So 0.75 m naught. But out of that 0.75 m naught, some percentage will go to column strip, some percentage will go to middle strip. What is the percentage that is going to column strip? So that depends on specifically on relative stiffnesses in different directions. So we will do that using this alpha F L2 by L1. Okay, so alpha F1 L2 by L1. Now it is different for interior negative moment. The distribution of the total moment, how much goes to column strip, how much goes to middle strip, that's not same for interior negative moment, positive moment, and exterior negative moment. It's different. So for interior negative moment, it depends on L2 by L1 value. So let's just go to this 8.10.5. I will show you 2019. We will open 2014. So as I was saying, M naught is Q L2 times Ln square. So it is given separately here. In interior negative moment is distributed this way. Before that, just one point. Okay, so other thing you have to note is L1. L1 is the direction in which you are considering the bending, and L2 is the other direction. Okay. Okay. So that's why if you're
Dr. Nathan,
yes.
In this exactly in this table, how alpha L2 over L1 could be 0?
Okay, so Yes, so let's go to alpha F1 calculation. So that is just for interpolation purpose. So here is alpha, so the beam stiffness divided by the slab stiffness. Of course, if there is no beam spanning on either sides, and if there is only slab, then you will not have any stiffness for the beam. But again, it will not be the case because uh, okay, so you can, let me just go there, where there is no beams. There is a case where you do not have any beams spanning in supporting the slabs on any of the edges. So let's go to, I think it is better on the slide. So here is the, so you sometimes may not have an edge beam. So there is just the slab. So in that case, your alpha will come out to be 0 because there is no beam in that direction. There is only a slab. So in that case, you will get alpha to be 0. And the deeper your beam, the more is the alpha. So is that, do you think that is clear or? See, alpha F is your beam stiffness IB by IS, right? So I think I had figure somewhere. Let me see, where is IB, where is IS? Okay, we still take an effective beam when we do it. So can you really have 0? So I think right now let's take the case that 0 to, yeah, you see, so for example, portion of column strip MU in beams. So how much of the column strip moment goes to the beam? So that is 0 means I think it should be the case where there is no beam, everything is going to the slab. So in the column strip, all the bending is carried by the slab alone and nothing is carried by the beam. But still, as you said, there will be an effective beam there. So I think if I clarify how to visualize this effective beam, it will become clear. Let me, okay, wait 1 moment. I'm coming. 1 moment. So let me just open one sheet where it will become clear what is the beam part of the column strip and what is the slab part of the column strip, and that's where this confusion may be coming in. Okay, so here is one example. So here is just a second. I don't think this. Yeah. So leave those. After fixing the faucet or the faucet, I will put back this. Let it stay there. Don't take those. Okay, so from here, let's take this particular example. Now this is so in the, let's take a long span direction, for example, here, LX. So our column size is 14 in long span, 14 in short span. Beam depth is 20 in long span, 20 inches in short span. And beam width is 14 by 14. Now, how we calculate alpha? Let's see here. Okay, here. So alpha F1 is I beam over I slab. Okay, so now I beam is coming from here. So moment of inertia of beam. This is the effective beam. So let's. So of course we know for T beam the beam is integral with the slab. Then for your T beam we know how to calculate the effective width. So this is from the okay. This is from here. Let me just open. So that criterion, I think you all may remember. So you can find some effective width of this T-beam based on the because of the non-uniform distribution in stress across the width and so on. So when we have the beam which is on the edge of the, or which is inside the column strip in our bending direction, then within that column strip, whatever moment we are assigning, some part of it will be carried by the beam. No, I need that one. Please. Sorry. Please. Just a second. Sorry. So out of whatever moment is going to the column strip, some part goes to the slab part of the column strip, some part goes to the beam part. Now the confusion is which is the slab part, which is the beam part. That's what I'm trying to explain here. So here in this example, for example, your slab thickness is 7 inches. So based on that, we can get some effective T-beam section for the beam, and we got our moment of inertia for the beam. And for the slab, our moment of inertia is just so this is BH cubed by 12, where this B we do take it as the full width in that span. Okay, so that means, okay, maybe I draw a figure that will make it. Okay. This is- So let's say let's say this is a column strip. And here, let's say column is same width. Let's say suppose there to there is the column strip. And let's say effective D-beam is here. Then then which part is going to the slab and which part is going to the beam? Okay. So for your slab moment of inertia, your alpha, your width will be the full, not just for the column strip, but you will take for the center to center. So that is the full width of that slab. So if you're doing bending in long direction, then the width in the short direction, that becomes your slab width in the short direction, or the span in the short direction, that becomes the width. So you will take that as B for BH³ by 12. So when will it become 0? Okay, let's take the case where there is no beam at all. Then, yeah, I guess that's the only case where you get 0. So you don't have any beam in the which is spanning the edges of the slab. So you don't have any beams connecting the columns. Let's say you just have flat slab. But in general, yeah, you can do flat slab design by direct design method too. So let me just make sure of that. I'll tell you that now. General flat slab is by equivalent method. That let me check the direct design. The direct design has the caveat okay. Okay, there is a caveat here. As you can see one of the criteria for applying direct design method is that this is for a panel with beam supports between all directions. Okay, so okay, this I will confirm. I think only in the case of flat plate, alpha will really be 0, or else you will always have some effective beam depth there, and it will not really be 0 there. Okay, so let me confirm this one. Don't mind. I will confirm it after the class. I will go and confirm it. That should be the case. Okay. Sorry. That should be the only case. Okay. So right now what we were going over is how much goes to the beam strip, how much goes to the column strip. Sorry, within the column strip, how much goes to the beam and how much goes to the slab. So the beam slab apportioning is according to these rules. So all of these, as we saw, they are from the ACI 318. Okay, this is just distribution coefficients, which we already saw earlier. This is portion of the moments in the column strip. And here, so within the column strip, how much goes to beams? So that's that is given by this table here. Go back to okay, yeah. So this is the only clause for that. Within the 8.10.5.7, within the column total moment carried by the column strip, how much goes to slab, how much goes to beam. So that's according to this criterion. So as Muhammad asked, so this should be 0 only in the case for a flat plate. I will make sure. I don't think in any other case it can be 0. Okay. So so here is a flow chart because there are various steps and details involved. So there is a, here I provided a kind of broad overview flow chart. So first step is always to check whether direct design method is applicable. And as we saw, there are various rules which we must follow. Main thing is that this main thing is that it's only for gravity load. Okay, so you cannot do it for use it for lateral load. Then you need to check your other span, long span to short span ratio. Then how many spans minimum in each direction, and then there is more. Unfactored live load shall not exceed 2 times unfactored dead load. I think Mercy mentioned, so some of those criteria may, when you have special cases of loading that may not be satisfying this. So most likely we will not be allowed to even use direct design method there. And yeah, when you do have beams between supports on all sides, then you must satisfy this condition for the alpha F1 L2 square by alpha F2 L1 square. When all these are satisfied, then we can use direct design method. Okay, so here is the basic flow chart. You first check whether all of those criteria are satisfied, then we can apply the direct design method. Then we, like we said, we go check our slab thickness, calculate our factored load, calculate total moment for both directions, then calculate from moment coefficients, what are the positive and negative moments, then distribute those to column strip and middle strip, then go design our reinforcement. So as you can see, it is a quite longer process. So what I did some earlier class, during some earlier classes, I made this sheet, and in this sheet, actually it is looking up all these values from the code automatically. For example, if you look at that, actually now I myself forgot how I wrote here. I remember a bit, but just give me a second to try and remember. I'm going to say where you need to write using VB. It's not that complicated, but I just want to show you where I wrote. I remember those. For example, this is beam moment. How much is going to beam? How much is going to the slab part of the column strip slab moment, column strip beam moment. Okay. So just a second. Because it's been a while, I forgot to where I wrote, but just a second. Let me see what way. What way. Oh, yeah, yeah, I think. Yeah, there should be a macros here. So first, let me send this sheet to all of you. Do anything. Because usually if we do it by hand, direct design method will take a long time. Okay, I sent those to you. Oh, by the way, there is one person. Yeah, Mohammed, have you tried contacting this Mr. Carl Hunter? Usually he is very fast to do things.
No, I didn't contact him. I
Yeah,
just talked
can you?
to Dr. Armwood. He
Uh,
talked to someone in the graduate office.
oh,
They had to be. They were supposed to give me the access,
uh,
but nothing happened.
can,
I don't.
nothing. Can you email Carl Hunter?
Okay,
See what is it?
okay.
C Hunter at. I will put it in the chat. Oh, thank you so much, Mercy. So you email him,
Thank
and
you
you
so.
can CC to Dr. C. Oh, because that they really took a long time. It's November. They still didn't give you access. And you CC to Dr. C, and you can just mention that you are in this course since 2 months, but you never got e-learn access.
Okay,
Okay. Okay.
okay.
So, okay. Now let me. Yes, Mercy. Thank you very much. Maybe we can take. Oh, okay. Great. So this is exactly relevant to. Let's just check out the abstract.
I would just read the conclusion.
Yeah, I was usually in the abstract, in the end of the abstract, there is some statement given, but here is okay. Since there are some two-way slabs, okay. Okay, so let's see what is he saying. Okay, so he is there. Okay, here is hey, so this one is the revised. Okay, so m equal to 2. So this is even different than ACI 318 2019, I guess. This thesis is from which year?
Was 14, I think.
Oh, this is 2009.
Oh.
So most likely, no, I mean, I'm sure that most likely, because for every cycle, they will review all of the most recent research and update it. See, this is very important you sent this because see, this was not there in 2009, I think, in the code. So like for example, the equation for this calculating average moment of inertia, she is saying that it may not be conservative, the one they're using. So they must have implemented something from this thesis maybe into the 2014. So usually they will, but sometimes if it is very recent, they may not. Like just let me, I know this is concrete class, but I just want to show one example. Uh, So for example, in the beam columns, we use this method for finding our equivalent load. So when we are doing second order analysis, it's not easy to just go by with load and moments in two directions and then start looking up which section satisfies. It will be more like trial and error. But this paper was quite recent. We used this. I think this is from 2018, 2019, this paper. So it is not yet there in the latest edition of AISC manual is 2017. So this update is not yet there in the AISC manual. So like that, I think right now, since we are using 2019 code, if there is any latest research, maybe it is not yet there. But you are right. Sometimes they could overlook even some of the old research. It may have something that is not, that was not maybe overlooked and not used in the code, because there is another reason too. They will also, it is not just based only on the theoretical correctness and experimental accuracy and all of that. Also, you see sometimes a lot of empirical method is favored, especially for concrete as compared to steel, because if we were to go for a very, like for example, see two-way slab, we are using direct design method. There is a lot of empirical part in that, but it is much more convenient for day-to-day use. Engineers need to do a lot of repetitive design two-way slabs. So sometimes the very strong, if there is very heavy theory, it may be adapted for everyday use. Like even LRFD itself, the LRFD method of design itself is, it came from probabilistic method of design. Now, if you go to probabilistic design, there is a lot of mathematics from probability there, but that is not very convenient for everyday use by engineers. So that's why it is adapted, but it's very correct. We need to keep checking whether that is.
Okay, I see what you mean, because empirical and not only theoretical too. Thank you.
No. It is this person. I think they have done a lot of experiments too. The paper that you sent, so it's very. Have you sent only to me or everybody? Maybe let me send to all of you. All of you can go through it. Oh, this is the undergraduate. All of you, please go through. Shall we last conclusions chapter? Is this to see the recommendations for thickness? I think they recommended 10% increase over what the ACI code is recommending. So we can.
I think it's also for two-way slabs, so kind of related.
Right, exactly, yes. Like it is for two-way slabs. So please check one thing, whether the recommendations provided at the end of this thesis, or maybe not all, whether any of them or all of the recommendations were implemented in ACI 318. Check.
It'd be 14 because it uses what our 2009. Maybe it should be
Yes, 2009. It should be 9. Yes, you are right. After O2, oh no, O5, and it was in O9. So, okay, it should be in 14.
14, yes.
After O5, O8 was there. That is O2. Yeah, there's 11, so it should have been 11. Okay. It's here 11 as compared to 18. I think before 11 was 05. 08. So 3 years. So you can compare 318.08 to 318.11 and check. Okay. I think the older ones should be available for free. Oh, by the way, I am not sure if all of you are took membership in ACI. I think for student membership, the price is not very high. You can take it, then you might be able to download the older one for free. If not, I will check and see. Okay. Okay. Now let's get back to we were in the macros. I think I should tell you also because when you start Excel, if you open this sheet, you may not see immediately the macros. So what to do there? And it is very useful. I think I wrote the comments also there. So it will be very easy to match with the code clauses. Let me show you. Let me tell you what I'm saying. I think we need to go to, you might need to do this too on your computer. More options. Things here. Yeah, here. View macros. Okay. Here's where they start from here. It's STR. Just a second. Sorry, it's been a bit of time, so I forgot. I think you need to press some key to access the macros. Check. F9 or something.
There's nothing recorded because there should be something under macro name. It should have a list of name.
No, it is. You see, it is active here. This is the name I made for each of those. For example, this is the.
Oh, your developer is not on. Is your developer on? Go to File, Option.
Oh, okay. That may be the. Yes, you're right. Yeah. Yes, there should be option here. Oh, here. I missed it last time.
And then Custom.
And then.
Custom
Oh, here.
ribbon. Yep.
Ribbon here.
Mm-hmm. And then check developer.
Okay. Thank you. Yeah, right. Okay, now maybe that's the.
And then view.
Yes. Probably view code. Yes. Yes. So here are the codes. Thank you so much, Mercy.
You're welcome.
Yes. So you can see. Thank you so much. So that's the one which wrote quite long back. So I even forgot how to access those. But there is for each of them, there is a code. You can access those. So this is each function has a code here. So let's run through this, what we did here. So first step is our so first step, we check all of the clauses, whether we are satisfying direct design method. Then yes, so say checked. So in this example, we have long span 25 feet. Long span is 25 feet, short span is 20 feet. You have column dimensions, beam depth, beam width, clear spacing. You will subtract out the column width there. So for clear spacing and long span, half column width on either side. So one full column width. From center to center, if you subtract half column width on either side, then you get clear span. Then this is your Lx by Ly ratio. So it is less than 2. So it is a two-way slab. Now, so then you look up your slab thickness. So I gave you the clause number here. I think. Okay, I haven't put a formula here. Then this is how many PSF your factored load for PSF. Then first we do the long span. So for long span, your short span, that is this one, becomes the converter from area load to line load. Okay. Then this is your span. That's your clear span in the long span direction. So divided by 8. So that is your design moment. Now here is your moment distribution factor. So from where do you get it? This I don't think I've put a code. So if you go to 8.4.10.2, think that is 8.10.4.2. Okay, here. Yeah, this is the table. Sorry, you can please fix that in your sheet. And so this particular example, it was for, so it is from the textbook. So you can compare whether whatever this code is giving, it is matching your answer there. This is for beams on beams supporting the slab on all edges. So here, this case falls under slabs with beams between all supports. So you can see here it is 0.7, 0.57, and 0.16 for exterior negative. So this was an exterior panel. So this is an exterior panel. That's what we are doing. That's what we are designing here. So along the long span, you have an exterior negative moment, positive moment, and interior negative moment. So exterior moment is exterior negative 0.16, interior negative 0.7, positive 0.57. So those are the yes. So those are the factors. So you just multiply whatever mu you got here by those. So now you got interior negative moment, exterior negative moment, and positive moment. Now we need to distribute these to beam strip and column strip. This is where a lot of these calculations come in, and the sheet becomes useful to you. Now, I calculated already the moments of inertia for the slab strips exterior panel as well as the interior panel. Now, exterior panel is moment of inertia is different because, let me explain to you. Okay, this one is for long span bending. Okay, so in the long span, if you see, this is the long span bending direction. So in the long span, the slab moment of inertia is the same. Okay, so it is the same as for the interior panel. If you see bending in this LX direction for this exterior panel and interior panel, your slab moment of inertia is actually the same. There is no difference. But if you see the short span, then your then if you come to short span, then for your okay, if you take this panel for example, And if you see short span bending, then for exterior panel, your moment of inertia is going to change. So just give me 1 second.
Dr. Nathan,
recall.
is there
Yes.
any difference between corner panel and
Yeah. Corner panel is, this is corner panel. Yes, both short span and long span, both will have, both of them will have exterior negative moment. But for this exterior panel, only the long span has an exterior negative moment. So just a second, I'm just telling you which one to use among these two. For this particular one, we will just need the slab beam strips, this moment of inertia calculated according to the full short span width and the slab thickness. But if you're looking at the exterior panel's slab beam strip, then we are only using half of this only half of the short span dimension. Okay, so why we are using only half is because okay, so let me explain right here. Maybe so when we are looking at a slab beam panel here, so this is one slab beam panel, center to center, this whole thing. Okay, and this is another slab beam panel. So when we are looking at this slab beam panel, we will take the full width in the short span to determine the slab moment of inertia. But when we are doing this panel, then we will use only half of this short span width to determine the slab moment of inertia. Okay, but when we are doing this one, we do take the full short span width. So I'm just saying, because in some places I might have given both, but we are not using this one in the calculations here. But if you go to the next one, which is for the exterior slab beam strip, yeah, so right from here, for everything, you see, for the moment, then for moment of inertia of the slab. Okay, if you look at my alpha calculation here, this alpha is based on, yeah, this is for interior panel. That's not what we will use. Exterior panel, this is what we will use here. So, I mean, the confusion is because in the Excel sheets, I have put both exterior and interior panel, but we are not using both. If you check the calculations carefully, for exterior slab beam width, interior panel, this calculation is irrelevant. So when you're using the sheet, if any irrelevant things, you can feel free to delete it out. It will not be used in the remainder of the sheet. Sometimes it's also I put there, so it could be a bit confusing. That's what I'm saying. Okay. Now. Okay, so now the main thing is first is the calculation of alpha and alpha F1, alpha F1 L2 by L1. So those are calculated here. Next one is calculation of the torsional stiffness of this beam. That is also a factor, as we discussed before, that's going to increase the bending stiffness in the perpendicular direction. So that's also automatically calculated here. So that's based on, we divide this T-beam effectively into boxes. Like you take only this flange, then you do XY for that, then only this, then you add up all of them. So that's what I've done here. That is done automatically. Then from there, this is the torsional stiffness C, and this is the beta T is the ratio of torsional stiffness of the beam to the slab's bending stiffness, flexural stiffness. So that is also here. Now is what is the step? So we have our moments from here: positive moment, negative exterior, and negative interior. So these have to be distributed to column strip and beam strip. So that's where the code comes in. And again, thank you very much to Mercy. I forgot how to view this. Okay. So now you can go there, check which I used here, beam strip position. Okay. So don't go to that one first. First check this and this. First check this and this column strip interior negative, and middle strip is just what is remaining from the column strip. So let's go check column strip interior negative, that code. Yeah, here it is. So we said that, okay, so you have for column strip interior negative, we are following this table. Here, okay. So alpha F1 L2 by L1 is where? Based on that, we will decide this value. So how is this implemented in the code? Now, each time looking up the code when you do direct design method by hand is really very painful process. So, here is the, you have two inputs. So one is alpha F1 L2 by L1 and L2 by L1. So as you can see, there is a double interpolation here. Then there is another one too, I'm going to explain. So first is the double interpolation, okay? So you first interpolate okay. Okay, you're just interpolating in the horizontal direction and in the vertical direction, okay? So first is your alpha F1 L2 by L1 is less than 1. If you notice the arguments here, if you go back here, B59 and B64 are the arguments. So this is L2 by L1 is the second argument, and alpha F1 is the first argument. Okay, so now go back there. Oops. So number one is alpha F1 L2 by L1. Yeah, so this is more than 0.5 and less than 1. Okay, then you the lower limit is 0.75. Upper limit will interpolate between 0.9 and 0.75, right? Then if this is between 1 and 2, lower limit will interpolate between 0.75, again, same 0.7. Upper will interpolate between 0.75 and 0.45. Else, if it is, this is 0.75 and upper limit is 0. Okay, if it is more than 2, if more than 2, upper limit is just 0. Let me just explain this. Number 2, alpha F1 L2 by L1 is more than 0.5, less than 1, that is this case. More than 1, less than 2, that is this case. Then the other case is just upper limit is 0. Okay, let me tell you what is that. Oh, okay, I will tell you what's that. Okay, that is based on, okay, then number 1 for L2 by L1. Okay, that's going between number 1 is 0, then just a second. It's been a while, so I just I made that a bit some time back, so I'm just recalling. But they're all made according to these tables. The tools. Oh, number 2 is L2 by L1. Okay, so yeah, first was all done as per L2 by L1. Then for number 1, if this is 0, then just 0.75. If this is less than 1, then you interpolate between upper limit and lower limit from here. And if not, you just take the upper limit. Okay, greater than or equal to 1, just upper limit. Okay, I think this case is not being used. Then there is one more. This Bx is how much is going to the beam. So this is coming from, this is everything distributed to column strip. Okay, how much percentage of mu is going to column strip. But out of that, how much is going to beam strip. So Out of that, how much is going to beam strip? That one comes from here. So distribution coefficient alpha F1 L2 by L1 is 0. Distribution coefficient is greater than or equal to 1, then 0.85. So how is that implemented in here? Okay. So again, our alpha F1 L2 by L1 is the value number 1. So if you see when value number 1 is 0, then 0. Okay. Nothing goes to the beam. Greater than or equal to 1, then 0.85 goes to the beam. If not, we interpolate. Okay. So that much is finally whatever is going to the beam, 1 minus that is going to the column. So you can see, let's do a quick hand check. For example, in this case, how much will be going to the column? So in our case, our alpha F1 L2 by L1, we are doing interior panel 2.38, okay? Beam by slab, 2.38. So in our case, alpha F1 L2 by L1 is more than 1. So from here, if you go portion of exterior negative moment in, okay, not exterior negative, portion of interior negative moment. Okay, so our alpha F1 L2 by L1 is more than 1. That's fine. And L2 by L1 is 0.8 for us. Okay. Yeah, L2 by L1 is 0.8. Now, if you go here and check, L2 by L1 0.8, so it will interpolate between 0.9 and 0.75. So if you do a quick interpolation, it will be 0.9 plus 9 minus 0.9 divided by so 0.81, okay? 0.81 is going to column strip. Now, out of that, how much is going to beam? Greater than 1. That means 85% is going to beam. So 85% of 81% is going to beam. So let's do that. 85% of 81%, 0.6885. Okay, so that much is going to beam. And how much is remaining? 15% of 81% is going to column strip, only the slab part. So 15% of 81 is 0.1215. Okay, so you see each time to do all this by going over all the tables for interior negative, exterior negative, positive, just will take too much time. So you all can just follow this sheet. Okay, but please be very careful. Like I said, somewhere I have double arguments. I have not used them. It should be okay, but be careful. Those are not used, some of them. Okay. Now, same way for positive, same way for exterior slab, interior slab beam strip and exterior slab beam strip. Now, for interior slab beam strip, here are the negative moments. You just multiply this coefficient with your mu value. Mu value is here, or I called it m0. So you just multiply by that. Then you will get all your moments. So these are your then design moments. Then you come here for each of those design moments. You convert to kip foot. You have the D, you have the B, and then you do your usual. This is just like looking up your reinforcement from your flexural resistance chart, or do just a hand calculation. Okay, so is this clear? Somewhat how we are using direct design method. We will go through a bit more. Maybe I might do a recording, but I will send one small assignment. You should not be having hand calculation anywhere except the last step where you assign your reinforcement area and number of bars. Okay. Till then, there should not be, till then all of part of approach positive movement, negative movement, positive movement, negative exterior, negative, interior, negative, positive, then distributing that between column strip and beam strip, then within the column strip distributing between beam and the slab part of the column. All of that is automated here. But please go over carefully, and then only the last part you need to do it by hand. So is that okay? You think that's okay? I will send you. I think I had one homework for that, and I'm going to send you that. I think it was just that in the Excel sheet I had done the interior slab beam strip. Okay, here exterior slab beam strip is done for you. Okay, so this was for this strip. So if you see the exterior slab beam strip, let's come back here. If you see interior slab beam strip in long direction, then there is an exterior movement and interior movement. But if you go to the short direction, then you will have a bit of a difference there, because your both sides are interior negative moment. You don't have any exterior negative moment. Let me just erase this. Almost getting there. Oh, I can't. Okay, so for example, this is our exterior panel, right? So for long direction, you have interior negative, positive, exterior negative, positive, interior negative. For short span, both are interior and this is positive. But on the other hand, for short span, you also have a exterior column strip and an interior column strip. Whereas for long span, both the sides are interior column strips. Have you see there's a lot of things going on here. Is it clear? When you do long span bending, then you have exterior negative moment, interior positive moment, and interior negative moment. But when you do short span, you have only interior negative moments on both sides. But on the other hand, in short span, you have an exterior column strip and you have an interior column strip. But for long span, both the sides are interior column strips. So what I've done here is interior slab beam strip I've analyzed for long span. You place also here I've analyzed exterior slab beam strip for I think short span. So whatever is missing here, like I'm missing interior slab beam strip for short span. Okay, so this is exterior panel. I've done long span here, short span there. I think I've done all of it here actually. So can you please do one thing? Same problem, everything same, just repeat it for interior panel. Okay, everything is same, but just repeat this one for interior panel. Is that okay? Can you do one assignment based on that? I'll send out an email, then we can stop there. Same, everything, take the load, same, everything else dimensions same, but just do the same thing for interior panel. So that will be one assignment. Let me reply as to the direct design Excel sheet. I think this is 4. Can we please do design for interior panel? You can use the same Excel sheet, just change the as used, change the values at each step to adjust for interior. Okay. Then all of the moment calculations and portion between column strips and slab part and strips should be automated. Only the end part for determining by hand. Or you can write a small code for that as well. Okay. Okay, so I will stop here for today. All right. Next week we will do equivalent frame. We will use SPB, SP slab. Okay.
Yeah. Thank you.
Thank you, Dr. Lee.
Okay, Dr.
Thank you. Okay.
Thank you.